Look up at the night sky. What do you see? A vast, endless expanse of darkness, punctuated by distant stars. But here's the thing, that darkness isn't just empty. It's alive with mystery, humming with questions that have haunted humanity for millennia. What is nothingness? Is it truly empty? Or is it hiding secrets we're only beginning to understand? Today, we're diving into one of the most mind-bending topics in physics, the science of nothing. The physics of nothingness, a history of empty space, isn't just a journey through the void. It's a story about how humans have tried to make sense of the nothing that surrounds us, shapes us, and might even be us. Think about it. Every time you take a step, you're moving through empty space. But is it really empty? Ancient philosophers argued over this. Some claimed the universe was a plenum, packed full of invisible matter, while others insisted it was a vacuum, a true void. Fast forward to today, and we're still wrestling with the same question. Only now we've got quantum mechanics whispering that even the emptiest space is seething with energy, particles flickering in and out of existence. It turns out nothingness might be the most interesting thing in the universe. So why does this matter? Because emptiness isn't just a scientific curiosity, it's the stage on which reality plays out. The way we understand nothing shapes how we understand everything, from the birth of the cosmos to the glue holding atoms together. Over the next minutes, we'll unravel how thinkers from Democritus to Einstein grappled with the void, how modern physics turned nothingness into a cosmic playground, and why the answer to what is empty space might rewrite the laws of reality itself. Buckle up, this isn't just a history lesson. It's a trip to the edge of human understanding, where the emptiest places hold the biggest surprises. Centuries before microscopes or particle accelerators, the battle over nothingness was already raging. Picture Democritus in ancient Greece, staring at sunlight streaming through a window and noticing dust motes dancing in the beam. That simple observation sparked a revolutionary idea. What if everything, even solid objects, were made of tiny, indivisible particles called atoms, forever drifting through infinite emptiness? His vision of the void wasn't just space between objects, it was the very canvas of reality. But then came Aristotle, nature's greatest cheerleader, who dismissed the void with a shudder. To him, empty space was an insult to the cosmos, a universe that overflowed with purpose and substance. His famous dictum, "Nature abhors a vacuum," wasn't just poetry. It was a scientific manifesto that would dominate Western thought for 2,000 years. What's fascinating isn't just their disagreement, but why they disagreed. Democritus, the radical materialist, saw emptiness as freedom, the blank page where atoms could dance and collide to form worlds. Aristotle, the biologist at heart, couldn't stomach the idea of purposeless space. To him, every inch of the universe had to do something to be something. This clash wasn't just about physics, it was about fear. The void terrified ancient thinkers because it mirrored existential dread. What if life, meaning, even the gods, were just temporary patterns in an endless sea of nothing? That terror seeped into science, turning the vacuum into a philosophical battleground. But the story gets richer when we look east. Half a world away, Buddhist and Taoist philosophers were embracing emptiness with open arms. In ancient India, the concept of shunyata, often translated as voidness, wasn't a scary absence but a profound truth. The universe wasn't empty in a hollow way. It was empty like a clear sky, full of potential. Meanwhile, Chinese Taoists saw the void as the mother of all things, comparing it to the hollow center of a wheel or a vessel, the very thing that made movement and function possible. These weren't just pretty metaphors, they were sophisticated takes on how absence defines presence. So why did the West struggle so hard with the void? Part of it comes down to tools. Without pumps or pressurized chambers, Aristotle's followers couldn't prove a vacuum existed. They could only argue from intuition. And intuition favored fullness because humans are wired to see patterns, not gaps. But deeper still, the resistance reveals a cultural fingerprint. Western science, at its birth, was obsessed with substance, with naming and categorizing what is. The idea that reality's foundation might be what isn't felt like a threat. Yet hidden in that tension was a seed. Democritus' atomic void, though ignored for millennia, would eventually sprout into modern physics proof that sometimes the most radical ideas just need time to breathe. The Middle Ages might seem like an unlikely time for a revolution in physics, but when it came to the void, thinkers were quietly dismantling Aristotle's ironclad worldview. Picture a medieval scholar hunched over a candlelit manuscript, wrestling with a paradox. If God was everywhere, how could true emptiness exist? Theologians argued that a vacuum would defy divine omnipresence. After all, how could the Creator tolerate a space where he wasn't? Yet, even amid these theological debates, curiosity flickered. In the Islamic world, the polymath Al-Hazen turned his genius to optics, probing the nature of light and space. His experiments hinted at something radical. Light could travel unimpeded through what seemed like nothingness, suggesting emptiness wasn't just possible, it might be necessary. Then came the Renaissance, and with it, a tool that would crack Aristotle's cosmos wide open, the barometer. Evangelista Torricelli, a pupil of Galileo, filled a glass tube with mercury and inverted it into a dish. To everyone's astonishment, the mercury didn't pour out completely, it left a gap at the top. That gap was a vacuum, the first ever artificially created on Earth. The implications were earth-shaking. Here was irrefutable proof that nature didn't abhor a vacuum. It simply balanced forces in ways Aristotle never imagined. Torricelli's experiment didn't just defy ancient dogma. It revealed a universe where emptiness had rules, where the absence of matter could be measured, manipulated, even used. Suddenly, the void wasn't a philosophical abstraction. It was a laboratory reality. What's striking about this era is how science and spirituality collided over the void. The same church that condemned Galileo for heresy found itself grappling with Torricelli's vacuum. Was it sinful to create emptiness, or was it a testament to human ingenuity? Meanwhile, alchemists and natural philosophers began to see the void as a kind of alchemical crucible, a space where transformation could occur, free from the clutter of matter. This wasn't just about air pressure or mercury columns, it was about redefining the very fabric of reality. The void became a mirror reflecting humanity's growing confidence in reason, yet also its lingering awe at the unknown. By the time Isaac Newton entered the scene, the void had shed its mystical baggage and become a scientific frontier. Newton's absolute space, a vast, unchanging emptiness, wasn't just a backdrop for celestial mechanics, it was the silent partner in gravity's dance. But even then, the mystery lingered. If space was truly empty, how could forces like gravity act across it? The stage was set for a new kind of revolution, one that would take the void from being merely empty to being alive with hidden potential. The battle over nothingness was far from over, it was just getting started. The 17th century didn't just tinker with the idea of emptiness, it tore apart the old rules and rebuilt them from scratch. Enter Robert Boyle, a man obsessed with air, or rather, the lack of it. His infamous air pump wasn't just a gadget, it was a theater of revelation. Picture this, a bell ringing inside a glass chamber as Boyle's team slowly sucked out the air. At first, the sound was clear, but as the vacuum took hold, the ringing grew fainter, then silent. That silence wasn't just absence, it was proof. Sound needed matter to travel, meaning true emptiness had a voice, or rather, the lack of one. Boyle's experiments did more than debunk ancient myths. They gave the void a language of its own, written in the dialect of experimentation. But the real shock came when Isaac Newton stepped onto the stage. While Boyle played with jars and pumps, Newton looked to the heavens and saw emptiness as the universe's scaffolding. His concept of absolute space was radical, a vast, unchanging void where celestial bodies moved like actors on an invisible stage. Gravity, that mysterious force, could reach across this nothingness without any material medium, defying common sense. Imagine the audacity. Space wasn't just between things, it was an entity itself, silent and infinite, the canvas on which physics painted its laws. Newton's void wasn't passive, it was the silent conductor of cosmic order. What's fascinating is how these breakthroughs reshaped humanity's cosmic identity. For centuries, people saw the universe as a nested series of spheres crammed full of celestial matter. Now, the void wasn't an anomaly, it was the norm. The Earth wasn't the center of a crowded cosmic dance. It was a speck adrift in an ocean of emptiness. This shift wasn't just scientific, it was existential. If the universe was mostly void, what did that say about humanity's place within it? The answer was both humbling and electrifying. We weren't trapped in a finite, stuffy cosmos. We were floating in a frontier of infinite possibility. Yet, even as Newton's absolute space dominated physics, whispers of dissent began to stir. If gravity could act across emptiness, what was it? The void, once a passive backdrop, started to feel suspiciously active. Like a detective noticing clues in a cold case, scientists began to wonder, was empty space truly nothing, or was it hiding something far stranger? The stage was set for a showdown that would take the void from being a silent witness to the star of its own mystery. The age of modern physics was dawning, and with it, a revelation nothingness might be the most crowded place of all. By the 19th century, scientists faced a cosmic riddle. If light was a wave, what was it waving in? The answer seemed obvious: the luminiferous ether. This invisible, all-pervading substance wasn't just a guess, it was a necessity. Think of it like sound traveling through air or ripples crossing a pond. Without a medium, how could light zip across the void of space? The ether wasn't just a scientific placeholder, it was a comforting illusion, a way to cling to the idea that the universe was full, even in its emptiest corners. Physicists pictured it as an intangible ocean, its currents gently guiding starlight to Earth. Then came Albert Michelson and Edward Morley, two men with a contraption that would turn physics upside down. Their interferometer, a delicate maze of mirrors and light beams, was designed to catch the ether in action. Here's how it worked. If Earth was swimming through this invisible medium, like a fish through water, the speed of light should change depending on the direction it traveled. But when Michelson and Morley fired up their device, the results were baffling. No matter how they turned it, no matter how precise their measurements, the speed of light stayed stubbornly, impossibly constant. The ether wasn't just elusive, it was non-existent. The implications were staggering. For centuries, science had treated space as a stage, with the ether as its unseen floorboards. Now the stage was gone, and the actors' planets, stars, light itself were floating in a void with no anchor. The shockwaves reached a young patent clerk named Albert Einstein, who saw in this failure not a crisis but a clue. If light didn't need a medium, then maybe space wasn't a thing at all. Maybe it was a relationship, a flexible fabric where time and distance stretched and squeezed. His theory of relativity didn't just dismiss the ether, It rendered it irrelevant, replacing absolute space with a cosmic dance where emptiness bent and warped. What's fascinating isn't just that the ether was wrong, but why it felt so right. Humans are wired to fill gaps, to insist that every action needs a tangible cause. The ether was science's way of avoiding the vertigo of true nothingness, yet its downfall revealed something far more profound. Emptiness isn't a lack, it's a feature. The universe doesn't just tolerate the void, it uses it, crafting laws where space and time twist into knots and light defies common sense. Michelson and Morley didn't just fail to find the ether, they accidentally proved that reality is stranger, wilder, and more elegant than anyone had dared to dream. Einstein didn't just change how we see space, he revealed that the void itself is a cosmic sculptor. Picture space-time not as a blank stage but as a trampoline, warping under the weight of planets and stars. A bowling ball placed on that trampoline creates a dent, and marbles rolled nearby will spiral inward, not because of some invisible force, but because the fabric itself is curved. That's gravity in Einstein's universe, emptiness bending into shapes that guide the motion of everything. The nothingness between celestial bodies suddenly had a job description: flex, stretch, and dictate the rules of motion. But the real shock came when Einstein's math predicted something even wilder: ripples in spacetime itself. Imagine tossing a pebble into a pond. The waves that spread outward are like gravitational waves, vibrations in the void caused by cataclysmic events like colliding black holes. For decades, this idea seemed like pure theory. Then, in 2015, the LIGO Observatory caught one of these ripples passing through Earth, stretching and squeezing space by a fraction of an atom's width. Think about that for a second. Emptiness isn't static. It moves, carrying energy and information across the universe like whispers in a cosmic telephone. What's even more mind-bending is how this reshapes our oldest questions. Philosophers once debated whether a vacuum could exist. Now we know it's not just real, it's dynamic. The void isn't a passive container. It's an actor in the universe's grand play, bending light around galaxies, stretching time near massive objects, and echoing with the aftershocks of ancient collisions. When astronauts float in what looks like empty space, they're actually surfing a sea of invisible geometry, where every star and planet leaves its fingerprint on the fabric of reality. Yet here's the twist: Einstein's spacetime, for all its brilliance, still clings to one old assumption: that emptiness is smooth. Enter quantum mechanics, the rebel science that insists the void isn't tranquil at all. It's a seething foam of particles popping in and out of existence, a quantum frenzy that makes spacetime look less like a trampoline and more like a bubbling cauldron. The clash between these two visions, Einstein's orderly curves and quantum theory's chaotic froth, is the greatest unsolved puzzle in physics. The void, it seems, still has secrets to spill. So next time you gaze at the night sky, remember, you're not just looking through space, you're looking at it, a living, breathing entity that bends, ripples, and hums with hidden energy. The true magic of Einstein's revelation isn't just that emptiness is flexible. It's that the universe writes its deepest laws not in matter, but in the invisible folds of nothingness itself. If Einstein's relativity painted space as a smooth, bending fabric, quantum mechanics grabbed that canvas and splattered it with wild, unpredictable color. Here's the twist: what we call empty space is anything but empty. At the tiniest scales, the void is a churning ocean of activity, where particles flicker into existence and vanish faster than the blink of an eye. These aren't just theoretical ghosts, they're virtual particles, and their existence is written into the universe's deepest rulebook. The key lies in Werner Heisenberg's uncertainty principle, a cornerstone of quantum theory that reshaped our understanding of nothingness. Imagine trying to measure a hummingbird's exact position and speed at the same moment. The more precisely you pin down one, the fuzzier the other becomes. Heisenberg revealed that energy and time dance to the same uncertain rhythm. In empty space, this allows tiny bursts of energy to appear borrowed from nowhere, materializing as particle-antiparticle pairs before vanishing back into the void. It's as if the universe runs on a cosmic tab, constantly overdrawing its account but always balancing the books in the end. What's astonishing isn't just that this happens, it's that these ghostly particles have real-world consequences. Take the humble atom. Why don't electrons spiral into the nucleus like planets crashing into the sun? Quantum emptiness provides the answer. Virtual particles swarm around the electron, creating a protective buffer that keeps atoms stable. Without this seething quantum foam, matter itself would collapse. Even more mind-bending is Hawking radiation, where black holes, those infamous cosmic vacuums, leak energy because virtual particles near their edges get torn apart, with one swallowed and the other ejected into space. The void isn't just alive, it's generative, birthing phenomena that shape the cosmos. But the real magic lies in how this reshapes our oldest metaphors. For centuries, emptiness was seen as passive, a blank slate or an absence. Quantum mechanics flips that script. The void is more like a simmering pot of water, bubbles constantly forming and popping on its surface. Those bubbles might be fleeting, but their collective energy is vast. In fact, if you could somehow weigh empty space, you'd find it brimming with this latent power, so much so that quantum fluctuations might hold the key to dark energy, the mysterious force accelerating the universe's expansion. Yet for all its creativity, the quantum void also poses physics' greatest headache. When theorists calculate the energy of all these virtual particles, the numbers spiral into absurdity, predicting a universe that should have torn itself apart. This vacuum catastrophe reveals a crack in our understanding, a sign that somewhere between relativity and quantum mechanics, we're missing a vital piece of the puzzle. The void, it seems, is still the ultimate teacher, humbling us with its contradictions even as it dazzles with its ingenuity. So next time you think of empty space, don't picture a barren wasteland. Picture a cosmic loom, weaving reality from threads of fleeting energy. Those momentary particles aren't glitches, they're the universe's way of whispering that nothingness, far from being inert, is the most restless, inventive force of all. 1998 should have been just another year in astronomy, until two teams of researchers pointed their telescopes at distant supernova and saw the impossible. These exploding stars, cosmic mile markers for the universe's expansion, weren't just receding from us, they were accelerating, as if some invisible hand were giving the cosmos an extra push. The culprit, dark energy, a force woven into the fabric of empty space itself, stretching the universe apart faster with every passing moment. Think about the absurdity of this for a second. Empty space isn't supposed to do anything. It's the background, the stage, the silent observer. Yet here it was, behaving like an over-efficient stagehand, not just keeping the lights on but actively shoving galaxies away from each other. The numbers are staggering. Dark energy makes up roughly 68% of the universe's total energy budget. That's more than twice the contribution of dark matter and 50 times the influence of ordinary matter, the stars, planets, and galaxies we actually see. The void isn't just present, it's dominant, calling the shots in a cosmic drama where visible matter is little more than a sideshow. So what is dark energy? The leading candidate comes straight from Einstein's playbook, the cosmological constant, a term he once called his greatest blunder. Originally tacked onto his equations to keep the universe static, it later resurfaced as a description of vacuum energy, the hum of quantum fluctuations in empty space. But there's a problem. When physicists calculate how much energy these quantum jitters should contribute, the result is 10 to the power of 120 times larger than what dark energy observations show. That's not just a rounding error. It's the worst mismatch in the history of science, a glaring sign that we're missing something fundamental. Alternative theories scramble to fill the gap. Some propose dark energy isn't constant at all, but a dynamic field slowly evolving over time, a modern cousin of the ether, perhaps. Others suggest gravity itself behaves differently on cosmic scales, bending the rules Einstein laid down. The wildest ideas flirt with extra dimensions, where the force we perceive as dark energy leaks in from hidden layers of reality. What's fascinating isn't just the diversity of explanations, but what they share, a recognition that empty space is active, a participant in the universe's fate rather than a passive backdrop. The stakes couldn't be higher. If dark energy keeps accelerating expansion, the cosmos faces a grim destiny, the Big Rip, where galaxies, stars, and even atoms are torn apart by the void's inexorable push. But if the force weakens over time, gravity might yet rally, pulling everything back into a fiery collapse. Or perhaps the universe will strike a balance, expanding just fast enough to avoid catastrophe. Right now, we're like sailors trying to predict a storm's path while blindfolded, with only the faintest clues to guide us. Here's the twist: dark energy didn't have to exist. In a different universe, empty space might have been truly inert, leaving gravity to slow expansion steadily. That it doesn't, that the void is alive with this mysterious pressure, hints at deeper laws we've yet to uncover. Every time we peer into the night sky, we're witnessing a tug of war between two invisible giants, gravity's embrace and dark energy's push, with the fate of everything hanging in the balance. The greatest irony, the emptiest places, the voids between galaxies, might hold the master key to understanding it all. Black holes aren't just objects in space, they're places where space itself unravels. Picture the event horizon, that invisible boundary where gravity's grip becomes so fierce not even light can fight free. Cross it, and the familiar rules of physics dissolve. Time slows to a crawl, stretched like taffy by the black hole's immense pull. But the real mind-bender lies deeper at the singularity, a point where matter is crushed into infinity, where space and time cease to have meaning. This isn't just emptiness, it's the erasure of reality's very framework. What makes black holes so paradoxical is how they transform nothingness into a cosmic forge. Take Hawking radiation, the eerie glow predicted by Stephen Hawking in 1974. Quantum mechanics tells us that empty space isn't truly empty. It's a seething quantum soup where particle pairs constantly blink in and out of existence. Normally, they annihilate each other instantly, but near a black hole's event horizon, something wild happens. One particle gets swallowed while its twin escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this slow leak causes the black hole to evaporate, turning the ultimate symbol of destruction into a fountain of particles. Nothingness, it seems, can birth something after all. Yet black holes aren't just cosmic recyclers, they're also the universe's most efficient shredders. The no-hair theorem suggests that no matter what you toss into a black hole, whether a library of books or an entire star, it gets reduced to just three properties: mass, spin, and charge. All other information vanishes, as if the universe has hit the ultimate delete key. This idea sparked the infamous black hole information paradox, pitting quantum mechanics against relativity in a battle that's still unresolved. Does information truly disappear, or is it somehow preserved in ways we can't yet fathom? The void, it turns out, guards its secrets fiercely. Perhaps most astonishing is how black holes warp our understanding of emptiness. In everyday life, a vacuum is just space with the air pumped out. But near a black hole, emptiness becomes an active participant in reality's drama. The curvature of space-time grows so extreme that forward and backward lose all meaning. Even causality, the bedrock of physics, breaks down at the singularity. It's as if the universe has written a check that nature can't cash, a place where mathematics itself screams in protest. And yet, for all their destructive power, black holes might be essential cosmic architects. Supermassive ones anchor galaxies, their gravity shaping the orbits of billions of stars. Some theories even suggest that black holes could be portals to other universes, or the seeds from which new ones grow. From absolute nothingness springs infinite possibility. The lesson, emptiness isn't the end of the story. It's the blank page where the universe writes its next chapter. Quantum field theory gives us a universe where empty space should be bursting with energy, an unimaginable 10 to the power of 120 times more than what we actually observe. That's not a minor rounding error. It's like predicting the ocean should boil, only to dip a thermometer and find it's ice cold. This jaw-dropping mismatch, known as the Vacuum Catastrophe, isn't just a technical hiccup. It's a flashing neon sign that our understanding of nothingness is missing something monumental. To grasp how bizarre this is, picture a quantum field as an infinite grid of springs, each vibrating with potential energy. Even in their lowest energy state, these springs never fully settle. They jitter with what's called zero-point energy. Add up all that microscopic jittering across the cosmos, and the total should be enough to rip space-time apart. Yet when we measure the universe's actual vacuum energy via dark energy's gentle push on galaxies, it's almost laughably tiny. The discrepancy is so vast, it's as if every star in the night sky vanished overnight, leaving behind a single candle flickering in the dark. Why does this matter? Because vacuum energy isn't just an abstract number. It's woven into Einstein's equations as the cosmological constant, a term representing the energy density of empty space. Get this value wrong, and the entire universe's fate is miscalculated. The fact that our predictions are off by a factor of 1 followed by 120 zeros suggests one of two things. Either we've misapplied quantum field theory in ways we can't yet see, or there's a cosmic cancellation mechanism so precise it's like balancing a skyscraper on a needle's tip. Some theorists propose radical fixes like supersymmetry, a hypothetical framework where every particle has a twin that cancels out its quantum noise. Others suggest the vacuum's energy isn't fixed but dynamic, ebbing and flowing over cosmic time. The wildest ideas invoke the multiverse. In an infinite sea of universes, perhaps we just happen to occupy the one where vacuum energy is freakishly low, making life possible by sheer luck. Each theory is a Hail Mary pass, an attempt to reconcile math with a universe that refuses to follow the script. The vacuum catastrophe isn't just an academic puzzle. It's a humbling reminder that emptiness, far from being simple, might be the most complex frontier in physics. Every time we think we've pinned it down, it slips through our fingers like smoke, leaving behind questions that redefine reality itself. Absolute zero, the coldest temperature possible, where all classical motion grinds to a halt. But here's the quantum twist. Even in this frozen state, emptiness refuses to sit still. At -273.15 degrees Celsius, when every atom should be utterly motionless, space itself still hums with an irrepressible energy. This is zero-point energy, the universe's way of whispering that true stillness doesn't exist. Picture a pendulum hanging perfectly vertical, its weight absolutely at rest. In our everyday world, that's the end of the story. But in the quantum realm, even this rest is an illusion. The pendulum isn't motionless, it jitters imperceptibly, vibrating with a tiny but unavoidable energy that can never be drained away. This isn't a glitch, it's a fundamental feature of reality, baked into the fabric of existence by Heisenberg's uncertainty principle. The void isn't passive, it's a simmering cauldron of potential, where fields fluctuate endlessly, birthing particle-antiparticle pairs that flicker in and out of existence like cosmic fireflies. What's staggering isn't just that this energy exists, it's the sheer scale of it. Theoretical calculations suggest that a single cubic centimeter of empty space contains enough zero-point energy to boil all the oceans on Earth. Multiply that by the volume of the universe and the numbers defy comprehension. If we could tap into even a fraction of this power, we'd unlock energy sources beyond fossil fuels, beyond nuclear fusion, beyond anything we've ever dreamed. Imagine spacecraft propelled by the vacuum itself, or cities powered not by grids but by the boundless buzz of empty space. Yet here's the catch: zero-point energy is like a mirage in the desert, obvious in theory, maddeningly elusive in practice. The same quantum rules that create this energy also guard it fiercely. Most attempts to extract it run into the same wall. The energy is everywhere, but it's perfectly balanced, like a stretched rubber band with no loose end to pull. Some researchers have toyed with theoretical loopholes like the Casimir effect, where two metal plates placed incredibly close together can block certain quantum fluctuations, creating a tiny, measurable force. It's a hint that the void might someday be coaxed into sharing its riches, but for now, it's like trying to bottle lightning with a sieve. The deeper irony. Zero-point energy might hold the key to some of physics' greatest mysteries. Dark energy's relentless push on the cosmos could be the large-scale echo of these quantum whispers. The same vacuum fluctuations that frustrate engineers might be the invisible hand shaping the universe's fate. And if we ever crack the code, the implications would ripple far beyond energy production. We'd be rewriting the rules of reality itself. So the next time you hear the phrase empty space, don't think of a barren wasteland. Think of a cosmic battery charged to infinity, waiting for a civilization clever enough to flip the switch. The universe's greatest power source isn't in stars or atoms, it's in the nothingness that holds them all together. Here's something that sounds like science fiction but is laboratory fact. Place two ultra-thin metal plates a hair's width apart in a vacuum, and they'll snap together as if tugged by invisible strings. This isn't magic, it's the Casimir effect, one of quantum physics' most startling party tricks. The culprit, so-called empty space itself, which isn't empty at all, but crackling with fleeting bursts of energy that can literally move objects. Picture the quantum vacuum as a stormy ocean, where particle-antiparticle pairs constantly rise and vanish like bubbles in foam. Normally, this chaos is perfectly balanced, but squeeze space tight enough and the symmetry breaks. When those metal plates get closer than a micrometer, they act like cosmic bouncers, blocking certain wavelengths of quantum fluctuations from forming between them. Outside the plates, the vacuum's endless froth continues unabated, creating a pressure differential that pushes the plates together. It's as if nothingness itself has a preference, a subtle nudge toward order in the midst of quantum chaos. What's wild isn't just that this happens, but how it challenges our definitions. Forces usually come from something: gravity from mass, magnetism from spinning electrons. The Casimir force emerges from the absence of certain quantum possibilities. It's like standing in a crowded room where two people suddenly step aside, and the imbalance of whispers somehow shoves you forward. This effect isn't a laboratory curiosity. It's proof that emptiness has structure, rules, even a kind of texture. And here's where it gets practical. In the squeaky clean world of nanotechnology, where engineers manipulate atoms like microscopic Legos, the Casimir effect is both a tool and a nuisance. On one hand, it can cause tiny machine parts to stick together unpredictably, a headache for designers of microscopic gears or sensors. On the other, savvy researchers are harnessing it to create frictionless actuators and even quantum levitation devices. Imagine a computer chip where components float on the invisible pressure of vacuum fluctuations, eliminating wear and tear entirely. The deeper lesson. The universe doesn't recognize our tidy categories. Nothing and something aren't opposites, they're points on a spectrum with the Casimir effect as the bridge. Every time those plates click together, they're whispering a secret. Reality's true foundation isn't matter or energy, but the restless, creative void beneath them all. String theory takes the quantum foam and stretches it into something even stranger, a universe where emptiness isn't just seething with particles, but folded. Imagine space as a bedsheet, but instead of lying flat, it's crumpled into microscopic origami, with 6 extra dimensions curled up so tightly we'll never see them. What we perceive as empty, 3-dimensional space might just be the surface of a deeper, richer reality, one where gravity slips between dimensions like water through cracks in a dam. This isn't just about adding hidden directions to the universe. String theory's extra dimensions could solve the oldest rift in physics, the feud between gravity and quantum mechanics. In our familiar 3-dimensional world, gravity is the odd one out, weak and aloof compared to the other fundamental forces, but in higher dimensions it might finally join the party. Picture a hosepipe lying on the ground from far away. It looks like a simple line, but up close you see it's a cylinder. Similarly, gravity's feebleness in our world could be an illusion, its strength diluted across dimensions we can't perceive. The void, then, isn't empty, it's crowded, with gravity's full might vibrating just out of sight. The real magic lies in how string theory redefines nothingness. Particles aren't dots but tiny, vibrating strings, and their notes, their frequencies determine whether they're electrons, quarks, or photons. Even the vacuum hums with these strings, their lowest energy vibrations shaping the fabric of reality. But here's the twist, those hidden dimensions aren't random. They're calibrated, curled at precise scales to allow strings to resonate in ways that produce the universe we know. Get the dimensions wrong and atoms wouldn't hold together, stars wouldn't shine. The void in this light isn't a blank slate. It's a finely tuned instrument playing the symphony of existence. Yet for all its elegance, string theory has a haunting catch. We can't test it. Those extra dimensions might be too small for any experiment to probe, leaving the theory floating in a limbo between math and reality. Some critics argue it's not even science, just a beautiful story with no way to verify its truth. But supporters counter that the universe has surprised us before. After all, atoms were once just a philosophical guess, and black holes were mathematical curiosities before we found them. Maybe the void's hidden folds are waiting for their moment, biding time until some future Einstein unravels their secrets. So when you stare into the night sky, remember, the emptiness you see might be the ultimate sleight of hand. Behind the curtain of 3 dimensions, the cosmos could be writhing with unseen geometry, vibrating with strings too tiny to glimpse. The void isn't absence, it's the stage, the strings, and the sheet music all rolled into one. And if string theory is right, we're not just observers of this grand performance. We're part of its score. Bubble universes sound like something from a sci-fi novel, but they're a serious possibility in modern cosmology. Picture a frothing ocean where each bubble is an entire universe, floating in an infinite cosmic foam. Our cosmos might just be one of countless others, each with its own unique laws of physics, born from random quantum fluctuations in an eternal, seething void. This isn't just wild speculation, it's a natural extension of inflation theory, which suggests our universe ballooned from a speck smaller than an atom to its current size in a fraction of a second. If inflation can happen once, why not over and over, endlessly birthing new universes like bubbles in a boiling pot? The real shocker, some of these bubbles might be ticking time bombs. Meet the false vacuum, a state where empty space isn't truly stable, but trapped in a precarious balance like a marble resting on the peak of a hill. Right now, our universe seems to exist in what physicists call a low-energy vacuum, where particles and forces behave predictably. But if we're actually in a false vacuum, disaster could lurk in the equations. A single quantum event, a random fluctuation, a high-energy collision might nudge space into a lower energy state, unleashing a wall of destruction that races outward at light speed. In an instant, everything we know, atoms, stars, consciousness itself, could rewrite into something unrecognizable. Here's the chilling part, we wouldn't see it coming. The decay would move so fast, the first sign would be the end. No alarm, no warning, just an invisible curtain sweeping across reality, erasing the old rules and imposing new ones. The laws of physics themselves would shift, turning matter into alien forms or dissolving it entirely. It's the ultimate cosmic gambit. The universe might be balancing on a knife's edge, and we'd never know until it was too late. Yet even this apocalyptic scenario hints at something beautiful. If false vacuum decay is possible, it means the void isn't just empty, it's creative. New universes could bloom from the wreckage of old ones, each with different constants, different dimensions, even different forms of time. Our existence might be a fleeting eddy in an infinite river of realities, where every collapse births something stranger. The void, it seems, isn't just a destroyer, it's the ultimate alchemist, turning annihilation into genesis. So while the idea of bubble universes might feel unsettling, it also offers a strange comfort. If our cosmos is just one of many, then its quirks, the precise strength of gravity, the mass of an electron, aren't miracles. They're accidents of cosmic geography, frozen into place when our bubble inflated. And if the false vacuum ever does decay, well, somewhere in the foaming dark, another universe might be waking up, blissfully unaware that its existence began in our ashes. The void giveth and the void taketh away, and in that infinite cycle, even nothingness teems with life. Black holes don't just bend space, they might be rewriting the rules of reality itself. Imagine falling toward one's event horizon where time slows to a crawl. From your perspective, you'd cross that invisible boundary and be torn apart by tidal forces. But from an outside observer's view, you'd appear frozen there forever, your image smeared across the surface like cosmic graffiti. This paradox hints at something astonishing. Every bit of information about you, your memories, the atoms in your body, might get permanently etched onto the black hole's two-dimensional surface. Three-dimensional reality could be nothing more than a holographic projection, with emptiness itself acting as the ultimate hard drive. The math behind this is shockingly elegant. When physicists calculate the maximum amount of information a region of space can contain, they find it doesn't scale with volume, it scales with surface area. Picture a glass sphere. Classical intuition says its information capacity depends on how much you can cram inside it. But quantum gravity suggests the real limit is written on its outer shell, like a cosmic DVD where every Planck-sized pixel stores one bit of data. Apply this to black holes, and suddenly their event horizons become nature's most efficient storage devices, preserving information we once thought was lost forever. The void isn't empty, it's inscribed with the universe's deepest secrets. What's truly mind-blowing is how this reshapes our understanding of existence. If a black hole's interior can be perfectly described by data on its surface, maybe our entire universe works the same way. The stars, planets, and even your morning coffee could be holograms, three-dimensional illusions emerging from a two-dimensional code written on some distant boundary we can't perceive. It's as if reality is a video game and what we experience as space is just the rendered graphics, while the real action happens on a flat cosmic motherboard. Yet for all its revolutionary potential, the holographic principle isn't without controversy. Some argue it reduces consciousness to a side effect of information processing, stripping meaning from lived experience. Others counter that it elevates information to the fundamental fabric of reality, making the universe more like a grand cosmic thought than a collection of cold, dead matter. Either way, one thing's clear: the emptiest places, black hole horizons, the void between galaxies, might be where reality's source code is hiding, waiting for us to crack the cipher. So next time you gaze at the night sky, consider this wild possibility. The vast three-dimensional expanse above you might be a shadow, a magnificent illusion cast by information flickering at the edge of everything. The universe isn't just in space, space itself might be in the universe, a dazzling display projected from a deeper, stranger layer of existence we're only beginning to glimpse. Consider the odds. If the strength of gravity were just slightly stronger, stars would burn out in a cosmic blink. If the electromagnetic force were weaker, atoms couldn't bond and molecules would never form. Even the vacuum energy, that faint hum of empty space, is balanced on a razor's edge too much, and the universe would have torn itself apart before galaxies could take shape. This eerie precision isn't just coincidence. It's the anthropic principle in action. The universe seems tailor-made for life because, well, we're here to notice it. But that raises a haunting question: why does anything exist at all? One explanation is sheer, dumb luck. Among countless random universes with different constants, we just happen to emerge in the one where the numbers lined up perfectly. It's like winning the cosmic lottery, except the prize is existence itself. But the odds are so astronomically slim that some physicists suspect a deeper game at play. Enter the multiverse theory, where our universe is just one bubble in an infinite froth of realities, each with its own unique rules. In most, the constants are wrong and life never stirs. But in a rare few, like ours, the dice rolled just right. Suddenly, the fine-tuning isn't a miracle, it's inevitability, a statistical guarantee given enough rolls. Yet the multiverse isn't the only answer. Some thinkers propose a more radical idea. What if the universe had to produce observers? In this view, consciousness isn't an accidental byproduct but a fundamental feature of reality, woven into the fabric of physics. It's as if the void itself is set up to ask questions, to marvel at its own existence. This isn't mysticism, it's a twist on quantum mechanics, where observation collapses probabilities into definite outcomes. Could the universe exist because at some level it needs to be seen? The implications are dizzying. If the multiverse is real, our cosmic significance shrinks. We're just one of countless civilizations scattered across the foam of reality. But if consciousness plays a central role, the void becomes something stranger, a mirror reflecting itself through us. Either way, the anthropic principle forces a humbling realization. Emptiness isn't passive, it's participatory, a stage where the laws of physics perform a delicate dance, and we're both the audience and the choreographers. The question isn't just why there's something rather than nothing, it's why that something knows it's there. What if the universe's perfect mathematical order isn't a discovery but a design? The simulation hypothesis takes the eerie precision of physical laws and flips it on its head. Maybe empty space isn't fundamental at all. Maybe it's just the default setting of an unfathomably advanced computer, rendering the void because processing every atom in full detail would crash the system. Think of a video game where distant landscapes fade into low-resolution textures to save computing power. Could the vast cosmic emptiness be our universe's version of an optimization trick? This isn't just sci-fi speculation, it's an argument with philosophical teeth. Nick Bostrom, the Oxford philosopher who formalized the idea, points out that if civilizations eventually run ancestor simulations, the number of artificial minds would dwarf biological ones. Statistically, we're more likely to be among the simulated, and if that's true, the void takes on a new role, not as the canvas of reality, but as the unused RAM of a cosmic machine. Even quantum fluctuations, those particle pairs blinking in and out of existence, might just be background processes, tiny glitches in the code. But here's where it gets surreal. If we're in a simulation, the very laws we study, relativity, quantum mechanics, aren't truths but parameters, the speed of light, a hard-coded limit to prevent processing overload. Dark energy, a patch to keep the simulation stable as it scales. Even the holographic principle fits neatly. A 2D boundary storing 3D information is exactly how you'd optimize a virtual world. The most unsettling part, we'd have no way to tell. A perfectly crafted simulation wouldn't leave bugs, just consistent, elegant rules that feel like nature. Yet the hypothesis isn't bulletproof. Some physicists push back, arguing that simulating every quantum particle in a universe would require more energy than exists in that universe. Others counter that a mature civilization might use shortcuts, approximations, fractal algorithms, to fake realism without brute force calculations. And if empty space is just a placeholder, what does that say about consciousness? Are we NPCs in someone else's game, or is the simulator itself a kind of god? Whether you buy it or not, the simulation hypothesis forces a dizzying perspective shift. The void we've spent millennia studying might not be the foundation of reality, just the blank spots on a blueprint. And if that's true, the greatest scientific quest isn't to understand the universe. It's to reverse engineer the code. Jean-Paul Sartre stared into the abyss and saw possibility. For the existentialist philosopher, nothingness wasn't just absence, it was the raw material of human freedom. Picture a cafe table where a waiter performs his role with robotic precision. Sartre would argue that by clinging to this identity, the waiter denies the void at his core, the terrifying truth that beneath the job, the routines, the labels, there's no essential self dictating his actions. This existential vacuum isn't cause for despair, but liberation. If nothing defines us inherently, we're free to invent ourselves anew with every choice. The void becomes a blank check signed by our own decisions. Yet halfway across the world, Buddhist monks reached a startlingly similar conclusion through entirely different means. In meditation, they sought sunyata, often translated as emptiness, not as lack, but as the ultimate nature of reality. Imagine a wooden chair. At first glance, it's solid and independent. But look closer, it's made of wood from a tree crafted by hands, existing only in relation to everything else. The chair has no permanent, intrinsic essence, it's empty of separateness. This realization isn't nihilistic, it's the gateway to enlightenment. By dissolving the illusion of fixed identities, one touches the interconnected fabric of existence. Physics echoes these ancient insights in eerie ways. Quantum fields fluctuate in what we call empty space, particles winking in and out of existence like fireflies in a midnight void. The more we probe nothingness, the more it resembles Buddhist sunyata, a generative absence where distinctions between observer and observed blur. Even the Big Bang hints at this, all matter, energy, even space-time itself unfurling from a state modern cosmology describes as no space, no time. Whether through meditation or particle accelerators, the message converges. Reality's foundation might not be solid ground, but a dynamic, dancing emptiness. But here's where the paths diverge. For Sartre, the void was a call to action and anguished freedom demanding we create meaning in an indifferent universe. Buddhist traditions, by contrast, see emptiness as an invitation to release, to stop grasping at illusions and rest in the suchness of things. Physics straddles both views. Quantum vacuum fluctuations suggest creativity bubbling up from nothingness, while entropy's arrow points toward cosmic dissolution. The same void that births galaxies also swallows them in black holes. Perhaps the deepest lesson lies in this tension. Nothingness isn't one thing, it's a mirror reflecting our deepest questions back at us. Is the universe fundamentally empty, or is emptiness just another name for its infinite potential? The answer might depend on whether you're holding a philosophy text, a meditation cushion, or a telescope. One thing's certain, the more we explore the void, the more it reveals about everything else. A blank canvas can be more unsettling than any stormy landscape. In 1915, Russian artist Kazimir Malevich unveiled Black Square, a painting that shocked the art world, not for its complexity, but for its radical emptiness. A simple black quadrilateral on a white field, it wasn't just a painting, it was a manifesto. Malevich called it the 0 point of art, a deliberate void that stripped away all illusion, all representation, leaving only pure sensation. At a time when science was grappling with relativity and quantum uncertainty, artists were dismantling reality in their own way, asking the same haunting question: what lies beneath the surface of what we see? Literature, too, has long been obsessed with the void's existential weight. Samuel Beckett's Waiting for Godot stages two characters trapped in a barren landscape, filling endless time with chatter as they await a figure who never arrives. A play's power comes from what's not there, the absence of resolution, of meaning, even of basic narrative progress. Like physicists probing the vacuum's hidden energy, Beckett exposed the human struggle to find purpose in apparent nothingness. The dialogue loops, the scenery refuses to change, and yet, against all logic, the characters persist. It's as if Beckett was scripting the universe's own absurdity, where the void isn't just empty, it's expectant. Even music has its voids. John Cage's 4:33 consists of 4 minutes and 33 seconds of silence, or rather, the ambient sounds that emerge when an orchestra doesn't play. Premiered in 1952, the piece forced audiences to confront the noise of their own breathing, the rustle of programs, the creak of chairs. Cage's silence wasn't passive, it was a frame highlighting how emptiness shapes perception. In an eerie parallel, quantum physicists would later describe the vacuum not as true nothingness, but as a seething arena of potential, where particles emerge from the background hum of existence. What unites these artistic experiments is their refusal to let emptiness be inert. Malevich's Black Square isn't just a lack of imagery, it's a confrontation with the sublime. Beckett's tramps aren't merely waiting, they're performing the human condition itself, a dance of hope and futility. Cage's silence isn't absence, it's amplified presence. Science and art, it seems, arrive at the same revelation by different paths. The void isn't a static backdrop. It's a participant, a collaborator, even a co-author of reality. Perhaps that's why the void fascinates across disciplines. It's the ultimate Rorschach test, reflecting back whatever questions we bring to it. For physicists, it's a quantum froth begging for equations. For artists, it's a mirror held up to meaning itself. And for all of us, it's the silent partner in every observation, every creation, every moment of existence, the blank page that makes the marks visible, the pause that gives the note its shape. The void, in the end, isn't nothing. It's the space where everything begins. The vacuum chamber might seem like a humble tool, just a sealed container with the air pumped out, but don't let its simplicity fool you. This unassuming device is the unsung hero behind some of humanity's most groundbreaking achievements. Take space travel, for instance. Before a rocket ever leaves the launch pad, its components are subjected to brutal tests inside massive vacuum chambers that mimic the airless void of space. Metals warp, seals crack, and electronics falter under these extreme conditions unless engineers have accounted for every possible failure. The same emptiness that once terrified philosophers is now a critical testing ground, ensuring satellites survive the harsh environment where they'll operate. Without vacuum science, every Mars rover, every GPS satellite, even the International Space Station itself would be flying blind into a hostile abyss. But the magic doesn't stop there. Glance at the smartphone in your hand, and you're holding a product of nothingness. Microchip manufacturing relies on ultra-high vacuum environments to deposit layers of material just atoms thick onto silicon wafers. Even a single stray molecule floating in the chamber could ruin a billion-dollar batch of processors. Companies like Intel and TSMC use vacuum systems so pristine they make surgical theaters look cluttered. The result, transistors smaller than a virus, packed by the billions onto chips that power everything from medical devices to self-driving cars. It's a paradox. The emptier the space, the more complex the creations it enables. Then there's the world of materials science, where vacuums unlock substances that defy nature. Diamonds harder than any found in mines are grown in vacuum chambers, their carbon atoms arranged flawlessly without atmospheric contaminants. Metallic coatings applied in vacuum conditions protect jet engine blades from melting under temperatures that would liquefy steel. Even the humble light bulb owes its existence to vacuum tech. Edison's original design sucked out air to prevent the filament from burning up. Today, advanced versions like LED and OLED displays rely on vacuum deposition to create luminous layers thinner than a soap bubble. Perhaps most astonishing is how vacuum science fuels cutting-edge physics. Particle accelerators like the Large Hadron Collider use miles of ultra-high vacuum tubes to keep proton beams racing at near light speed without colliding with air molecules. The slightest contamination could scatter these particles like bowling balls hitting a sandpit, ruining experiments that probe the universe's fundamental laws. Meanwhile, quantum computers harness vacuum environments to isolate qubits from the slightest thermal noise, preserving their fragile quantum states long enough to perform calculations impossible for classical machines. The irony is delicious. Our most advanced technologies depend on creating and controlling nothingness. From the sterile voids of chip fabs to the artificial cosmos of space simulators, emptiness has become an industrial partner. What began as a philosophical debate, does the void exist, has transformed into a trillion-dollar engineering discipline. The next time you swipe a touchscreen or stream a video, remember, it's not just silicon and code at work. It's the silent, invisible power of nothingness, harnessed by human ingenuity to build the future. The next frontier of physics might not be in distant galaxies or massive particle colliders, but in the silent, seething void right under our noses. Laboratories around the world are preparing experiments that will probe empty space with unprecedented precision, hunting for cracks in our understanding of reality itself. One of the most tantalizing projects is the development of ultra-sensitive quantum vacuum detectors. designed to catch fleeting particles popping in and out of existence. These aren't just academic exercises. If certain theories are correct, we might discover that the vacuum's latent energy can be tapped, not with sci-fi warp drives, but through subtle manipulations of quantum fields. Imagine spacecraft that don't burn fuel, but instead surf the ripples of spacetime itself, riding the quantum foam like a surfer catching a wave. Meanwhile, dark energy remains the elephant in the cosmic room. Upcoming telescopes like the Vera-C, Rubin Observatory, and the Euclid Space Mission are mapping the universe's expansion with razor-sharp accuracy, searching for clues about whether dark energy's strength changes over time. If it does, the implications are staggering. A weakening dark energy could mean the universe eventually collapses in a big crunch. A strengthening one might lead to the Big Rip, where even atoms are torn apart. But here's the wildest possibility. If we can decode dark energy's rules, could we mimic its effects? Theoretically, manipulating vacuum energy on a small scale might allow us to stretch or compress spacetime, intentionally opening the door to artificial gravity or even time dilation chambers, where hours inside pass like seconds outside. Then there's the enigmatic Casimir effect, which could hold surprises beyond sticky metal plates. Recent experiments suggest that under extreme conditions, the quantum vacuum might exhibit negative energy, a bizarre state where gravity repels instead of attracts. While this sounds like fantasy, it's mathematically plausible and, if harnessed, could enable theoretical constructs like traversable wormholes or Alcubierre warp bubbles. NASA Eagleworks Lab has already dabbled in these ideas, testing propulsion concepts that leverage quantum vacuum fluctuations. The results so far are inconclusive, but the mere fact that such experiments are happening signals a shift. Physicists are no longer just studying empty space. They're asking how to engineer it, but the biggest revolution might come from an unexpected direction: quantum computing. By simulating vacuum states with qubits, researchers are uncovering patterns that classical computers could never resolve. These digital experiments hint at hidden structures in nothingness, geometric shapes and symmetries that could rewrite quantum field theory. Some speculate that the vacuum isn't random chaos, but a highly organized digital-like code, with particles emerging from deeper computational rules. If true, we might be on the verge of a theory of everything, not by building bigger colliders, but by deciphering the void's hidden programming language. The irony is poetic. For millennia, humans feared the void as a symbol of chaos and oblivion. Now, we're realizing it might be the most ordered, creative force in existence, a cosmic engine humming just beneath the surface of reality. Whether it leads to star-spanning travel or revelations about time itself, one thing's certain: the future of physics isn't in the stars alone, it's in the nothingness between them. Misconceptions about nothingness run deep, especially in pop culture, where empty space is often dismissed as just, well, empty. Hollywood sci-fi loves showing the void as a silent, static backdrop, a blank canvas for starships to zoom across. But reality is far stranger. Modern physics reveals the vacuum as a buzzing hive of activity, where nothing is actually a dynamic player in the universe's grand story. Think of it like the difference between a flat, lifeless desert and a coral reef teeming with invisible motion. Except instead of fish, it's quantum particles flickering in and out of existence at unimaginable speeds. One of the biggest myths is that a vacuum is truly empty. Early scientists like Aristotle believed nature abhorred a vacuum, but even they'd be stunned to learn just how wrong that idea is today. Quantum field theory shows that empty space crackles with zero-point energy, a baseline hum of activity that never stops, even at absolute zero. It's like tuning a radio to static between stations. What seems like noise is actually a symphony of quantum fluctuations. Laboratories have even measured this directly. The Casimir effect, where metal plates snap together in a vacuum, proves that nothingness exerts real, measurable forces. If space were just an inert stage, those plates wouldn't budge. Another common oversimplification, treating dark energy as just a placeholder for we don't know. While its exact nature remains mysterious, we do know it's a property of space itself, a kind of anti-gravity woven into the fabric of the cosmos. Imagine blowing up a balloon with tiny springs inside. As it expands, the springs stretch and push outward harder. That's dark energy in a nutshell. The emptier space gets, the more it pushes galaxies apart. This isn't some fringe idea, it's the leading explanation for the universe's accelerating expansion, backed by Nobel Prize-winning observations of distant supernova. Then there's the myth that black holes are just cosmic vacuum cleaners. In truth, they're more like quantum alchemists. Hawking radiation reveals how black holes transform emptiness into particles, slowly leaking energy back into the universe. Even their event horizons aren't mere points of no return. They're holographic surfaces where information gets scrambled and preserved like a cosmic hard drive. The void here isn't passive. It's an active participant in some of physics' deepest paradoxes. Why does this matter? Because misconceptions about nothingness distort our cosmic perspective. If we dismiss the vacuum as just empty, we miss its role in everything from atoms to galaxies. Quantum fluctuations in empty space may have seeded the universe's first structures. Dark energy's push could decide its ultimate fate. Even our tech, from microchips to MRI machines, relies on harnessing the void's peculiar properties. The next time you hear empty space, remember, it's less like a deserted warehouse and more like the invisible wiring behind reality's walls, humming with potential we're only beginning to decode. Harnessing the energy of empty space sounds like science fiction until you realize the stakes. Imagine a future where zero-point energy isn't just theoretical, but a practical power source. A single cubic centimeter of vacuum could hold enough latent energy to boil oceans, according to quantum calculations. If humanity unlocks even a fraction of that potential, the consequences would ripple across every aspect of civilization. Who gets to control this technology? Nations with the resources to build vacuum energy reactors would wield unprecedented influence, potentially rewriting global power structures overnight. The same void that birthed galaxies could become the ultimate geopolitical prize, sparking conflicts over access to what was once considered nothing at all. But the ethical dilemmas run deeper than resource wars. Manipulating the vacuum isn't like drilling for oil. It's tampering with the substrate of reality itself. Quantum fluctuations aren't just energy, they're the invisible scaffolding holding atoms together. Start extracting energy on an industrial scale, and could we accidentally destabilize the fabric of space? Theoretical models suggest that large-scale vacuum engineering might create localized distortions, like cosmic potholes in spacetime. Even more unsettling is the possibility of triggering a false vacuum decay, a catastrophic chain reaction where our universe's energy state collapses into a lower one, rewriting physics itself. The risk might be infinitesimal, but the penalty would be infinite, total annihilation of reality as we know it. Then there's the question of equity. Vacuum energy doesn't come with a map, it's everywhere. Unlike oil or rare earth metals, it can't be hoarded by controlling territory, but the infrastructure to harness it. That's another story. The technical hurdles are so vast that only a handful of nations or corporations might ever develop the capability. Would this lead to an energy monopoly dwarfing anything in history? Or could it force unprecedented cooperation, with humanity treating the quantum vacuum as a shared commons, like the oceans or atmosphere? The void doesn't care about borders, but humans do. Philosophically, vacuum energy forces us to confront our role in the cosmos. For millennia, we've exploited resources, forests, fossil fuels, even sunlight. But tapping nothingness is different. It's not taking from the environment, it's borrowing from the framework of existence. Indigenous cosmologies often view nature as sacred, something to be stewarded rather than dominated. Modern physics might be arriving at a similar conclusion through equations. The void isn't inert raw material, but an active participant in reality's balance. Exploit it recklessly, and we risk more than an environmental crisis. We risk unraveling the rules that let reality exist at all. Yet the allure is irresistible. Unlimited clean energy could end poverty, reverse climate change, and fuel interstellar travel. Imagine cities powered by the hum of empty space, or spacecraft surfing quantum fluctuations between stars. The same energy that birthed the universe could propel humanity's next chapter. But with such power comes responsibility, not just to avoid catastrophe, but to ask why we're seeking it in the first place. The void has been here since the beginning, patient and silent. Before we reach into it, we'd better decide what kind of civilization we want to become. There's something profoundly humbling about staring into the void, not just as a scientist or philosopher, but as a human being. Every culture has its myths about chaos, the formless dark from which creation emerges, and perhaps that's no accident. When we confront nothingness, we're forced to reckon with the limits of our understanding. Think of the first time you saw a truly dark night sky, far from city lights. The sheer scale of that emptiness doesn't just dwarf us, it redefines what matter even means. Against the cosmic backdrop, entire galaxies are specks. Yet here we are, fragile and fleeting, daring to map the abyss. That tension between insignificance and curiosity is where wonder lives. What's remarkable is how emptiness compels discovery. The vacuum isn't passive, it's an invitation. When medieval alchemists tried to banish air from jars, they weren't just tinkering, they were probing the boundaries of what reality could be. Fast forward to quantum physicists wrestling with virtual particles, and the pattern holds. The void doesn't yield its secrets easily. It taunts us with paradoxes like a Zen koan written in mathematics. Take dark energy. We've measured its effects with Nobel-winning precision, yet its nature remains elusive. That's the irony. The more we learn about nothingness, the more we realize how much we don't know. And that's not failure, it's fuel. But here's the deeper lesson. Emptiness isn't just a scientific frontier, it's a mirror. How we react to it reveals who we are. Some see the void and despair, like Pascal trembling before the infinite spaces. Others, like the astronauts who described Earth as a pale blue dot, find kinship in the vastness, a reminder that everything we love exists against impossible odds. The void doesn't care either way, it simply is indifferent to our dramas, and that's oddly freeing. If the universe doesn't owe us meaning, then we get to create our own. Maybe that's why artists and mystics have always been drawn to nothingness. From the silent pauses in Beethoven's symphonies to the minimalist brushstrokes of Zen calligraphy, absence isn't empty, it's pregnant with possibility. The same quantum jitters that birthed galaxies also echo in the white space of a poem, the silence between notes, the deep breath before a leap. The void isn't an end. It's the blank page where we scientists, artists, dreamers write our next question, and the universe, in its infinite patience, keeps turning the page. Now it's your turn to weigh in on this cosmic riddle, because the mystery of nothingness isn't just for physicists and philosophers. It's a puzzle that belongs to all of us. Think about it. When you close your eyes and try to imagine true emptiness, what do you see? Is it a blank void, or does your mind instinctively fill it with something faint light, distant echoes, the ghost of a thought? That tension between what we perceive as empty and what might be invisibly alive is at the heart of humanity's oldest debate. Some argue nothingness is a human invention, a linguistic placeholder for absence. After all, even the darkest patches of space teem with quantum activity. Others insist emptiness is real, that beyond particles and fields, there's a fundamental void math can't erase. Ancient Buddhist texts describe sunyata, the emptiness underlying all form, while Western logic treats the vacuum as a measurable state. But which feels truer to you? Is nothing just a word we slap on whatever we don't yet understand? Or is it the universe's default setting, the silent stage before the actors arrive? Drop your thoughts in the comments. Have you ever experienced true emptiness, or is it always an illusion? Maybe you've felt it in meditation, where thoughts dissolve into stillness. Or perhaps you're Team Aristotle, convinced nature leaves no room for true voids. Your perspective might spark someone else's aha moment. After all, this isn't just about physics, it's about how we, as tiny specks in a vast cosmos, make sense of the spaces between things. The conversation's been going for millennia, and now it's your turn to add your voice. So hit pause, jot down your take, and let's keep unraveling the enigma together. Whether you're Team Quantum Foam or Team Absolute Void, remember, the most fascinating discoveries often start with a simple question, and yours might be the one that shifts the debate. The comment section is your lab notebook, and the experiment is far from over. From the ancient Greeks debating atoms and the void to modern physicists measuring quantum fluctuations in a vacuum, humanity's obsession with nothingness has rewritten the rules of reality. Think about that for a second. Our relentless curiosity about emptiness has unearthed some of the universe's deepest truths, from the bending fabric of space-time to the seething energy hidden in empty space. The void isn't just a backdrop, it's the unseen architect of everything. Stars ignite, galaxies spin, and particles flicker into existence, all because of how nothingness behaves. This journey reveals a profound irony. The more we study absence, the richer reality becomes. Take black holes where space and time twist into oblivion, only to spit back hints about holographic universes. Or dark energy stretching the cosmos apart from the shadows. Even the humble atom relies on quantum vacuum fluctuations to keep electrons from collapsing into nuclei. Every breakthrough in understanding emptiness peels back another layer of the cosmos and of ourselves. After all, we're made of stardust, yes, but also of space. Atoms are mostly void, their solidity an illusion conjured by electromagnetic forces. You're literally made of nothingness, held together by invisible threads. So what's next? The frontier of nothingness is wide open. Will we crack dark energy's code, or harness vacuum energy to power civilizations? Could the void hold clues to unifying quantum mechanics and gravity? One thing's certain, as long as we keep questioning, the cosmos will keep surprising us. The greatest discoveries often start by staring into the abyss and realizing it's staring back, not with emptiness but with infinite possibility. If this dive into the physics of nothingness sparked your curiosity, don't let the conversation end here. Smash that like button, subscribe, and join us as we keep unraveling the universe's grandest mysteries. After all, the void isn't just out there. It's in you, in me, in every breath of space between us. And that's a story worth exploring together.